Hello, everyone. Welcome to this session. My name is Nelly Sattari. I'm the lead developer at Challenger and Microsoft Azure MVP.
My name is Stafford Williams. I am a lead consultant at Telstra Purple, previously known as Redify.
Yeah. So we are going to talk about Azure SignalR Service and getting thousands of concurrent connections at the same time. So what we are going to do today is not... Okay, cute. None of them work.
You got it.
Oh, okay, sorry, a bit of delay. So we are going to talk about a little bit about real-time applications in general, and then we are going to talk about scaling the real-time applications and see the problems and solutions, and then a serverless approach to get real-time functionality, and then we have a very cool audience interactive demo at the very end. Let me share one of my experiences before actually we go through the talk about real-time functionality to make sure that we are all on the same page in regards to real-time. So I work in Sydney, just around the corner in number 5 Martin Place, and we have a very luxury reception. So every week we actually buy a very big flower bouquet, which is really luxury and expensive. And at the end of the week, we are not going to throw it out. We actually put in a bid, and everyone across the company can jump to the website and bid the flower. So whenever I participate, I actually win the competition. And also my team members, because we all know the tricks. The thing is, when I opened the website for the first time, I realized that, oh my God, there's no real-time functionality in our website. It means that like 5 minutes or 2 minutes to the closing time, I just pop into the website and I took a very high technical solution, which is this one. So this helped me get the latest content periodically, quickly, and see who put how much bid. And then with a few cents differences, I just add a little bit of cents to the highest bid, and then I win the competition. That's the trick, which I know that it's not really fair.
So I think we're probably all developers in here, so we can get a little bit smarter and we can do something like this. This is a little piece of JavaScript. There's hands up if anyone knows what that true means in that piece of JavaScript. That true means get that data not from the cache but from the server. So that's just a piece of code that's doing pretty much what we saw on the other slide as well. Before we talk about real-time web, let's talk about how the web mainly traditionally works. If you've been around any time since about 1994, this should be familiar to you. A browser or our client connects to a server. We make a request to that server. It responds to that request, and then the connection is dropped. What we saw just on the previous slides was that over and over again. So real-time apps, however, are those that when that data is available on the server, we push it without having to continually poll or request that data.
So although it's really interesting to have the real-time functionality in many scenarios, it's actually essential for some others. The examples are any kind of social apps. You know that how pleasant it is to get the notifications quickly as they become available, right? Or maybe online dating. So nobody will date with someone who is not responsive. So it means that this is the main feature of online dating. You need to get the content immediately. Or any tracking applications, including tracking your Uber rides, tracking your shipping package, or maybe sometimes your kids in the school car. Or other than that, like online gaming, there are heaps of different variety of games that people sit and play together online, and you will lose the game if you have even 1 second's delay. Any kind of dashboards in general, like incident dashboard, security dashboard, flight dashboard, where you need to get the new content once any event is happening in the system. So in general, the applications with high frequency update and the applications which are designed based off event-driven architecture are the best candidate for having real-time applications. We actually talked about, the real-time samples and examples in general, but right here in this room, we can kind of improve or fix some solutions, fix some problems, or improve some experiences by using real-time functionality. We all know that technology loves to, include people with disability. So let's say this is a very big venue and room, so people at the end might not really easily see the slides, right? So one way is just helping them with this real-time functionality to easier get the slides and see them. I walk you through the experimental experience. So if you don't mind, please scan this QR code for me.
So if you're at the back of the room, you might have to zoom in a little bit, but otherwise you should be able to bring up your iOS or Android device, fire it at, or aim it at this guy right here, zoom in a little right at the top of your screen, a little pop-up will show in there, and you should be able to join. We've got at least one person has figured that out.
Do you want to do
there's some more. What we'll do whilst I continue to talk is I will go back to here. That barcode will stay on here for a couple more slides to let you join. Otherwise, we'll be showing that barcode again at the end when we show some further demos. So for those of you that have connected your devices, I'm hoping that you are seeing this slide on your phone.
We can see the slides. Everyone can see.
Cool.
Cool.
Awesome. So how do real-time apps work? Well, an approach that we took quite frequently between the 2000s to about 2010 was one called long polling. That is very similar to our previous slide with the HTTP requests on it, where we make that request to the server, and as long as that server has some data, or until that server has some data, we hold that request open, and when we've got that data, we close that connection. Now, the moment the connection is closed, we make the request again, and on that server, if there is no data at that time, we just hold that connection open pretty much indefinitely until some more data is available. So this is called long polling. It used to be the go-to to do this. Lots of people were pretty angry on the internet back in those days about how we were maybe abusing the HTTP protocol. If you remember older browsers, sometimes you might have seen the loading icon on the browser just loading forever. Some people might remember terms like Ajax, push, or comet, that kind of thing. And basically that's what that technology is. Let's jump forward about 10 years to HTML5, and this technology becomes available. This is server-sent events, and it's a little bit different. It came with HTML5. It's one-way communication, so it's from the server to the client. It's low latency, and what we're going to do is we're going to hold open a persistent connection so we don't have to keep requesting for that, to hold that connection open to the server. Lost it. Anyway, we'll continue by saying it's low latency, however, unsupported by Edge and IE. So not great for us. Here's a little diagram of how it goes. It's HTTP request and response like we saw before. There's that persistent connection that's going to be held open. And then as new data is available on the server, we're just going to push it rather than continuing to make new connections. Next, we'll talk about WebSocket, which is a little bit nicer. The main difference with WebSocket and why we like it so much is it's bi-directional. So this time, we're going to hold that connection open, and if we have data on the server or if we have data on the client, we can send it both ways across that connection. So the reason why we like these service-sent events and these WebSocket technologies is that we don't have to send headers with every message that we send. So we could just send little ones, little zeros, that kind of stuff, low latency, very, very cool.
So which one would you recommend to use?
To be honest, with browser support these days, lots of them do support WebSocket, but that hasn't always been the case. I don't know if I want to spend all my time implementing all three of them, but I don't know. What have you got for me?
Okay, let's go to the next solution then. So ASP.NET SignalR, as you might know, it's the open source library, which is really popular. And SignalR shipped with ASP.NET originally. And basically, it comes around to simplify adding real-time functionality to your web applications. That's the reason it came around. And the best benefit of this library is it under the hood, it actually knows how to pick the best transport method for your, based on the like client capability and server capability. So you don't need to provide 3 different code base. With one code base, it actually provides the proper transport method for you. So if WebSocket can be available, so good. Otherwise, it will gracefully fall back to the other ones, like the long polling or server sent error event. So 2011, it was originated by David Fowler and Damien Edward, who were supposed to be in this conference. I'm not sure if he is. No, he is not. And another good thing about this library is that it actually provides the server-side and client-side library for us, because we have to have 2 different code base for server-side and client-side. And the new version of the SignalR shipped with ASP.NET Core. And it's completely a rewrite. It means that some features are changed, and if you have the legacy application with ASP.NET SignalR, you cannot easily shift it to ASP.NET Core, and you will have some breaking changes. So you need to manage that. Let's get back to our bidding example that I told you in the beginning. And as I told you, it's not really fair to have sit and press F5, because not everybody knows this functionality. So you might win the competition always. So we actually provided a quick POC kind of demo. I'll show you here. So this is a quick, simple application, which was written by Vue.js in the front side and ASP.NET Core on the back side, and then it's deployed to Azure. So I refresh the page. I pop into the website. So I ask Stafford doing the same thing. So, OK. So immediately, whoever joined the website, you can immediately see that who joined. And then whatever we put as a bid.
Same.
OK, let me beat you.
You win.
OK.
Again.
So we don't really need to, like sit and press F5. So whoever placed the bid, everyone just immediately can see how much it is. And it's fair, it's transparent, and everyone has the equal kind of access. I'll show you how we provided this demo, which is a simple demo. So you just need to install, pull down the SignalR library and then inject it to your ASP.NET Core application. Then the next step, I assume you still have it on your mobile. So if it's not really big, you can look at your mobile. The next step is just defining a route for the clients to connect to this route. Then the clients will fall over to this class, which is the hub class. So all the methods in this hub class are publicly available for the clients. So basically, they can send their message and ask the server to broadcast this message to all clients, as you can see here, or a group of clients, or maybe just one client. So the server will handle it and broadcast the messages and new content for you. Then we deployed this ASP.NET Core to Azure. I used Azure App Service. And we get back the URL, which we can use it in the client side.
So on the client, we're going to use npm to install our client-side library. We're using ASP.NET Core SignalR. So if you remember the older version of SignalR, the client library was shipped with NuGet, not amazing for JavaScript. This time it's on npm. That's all good. We add it with our into our packages.json, and then we can set up the hub connection and connect to that URL that we just saw Nelly deploy to Azure. There's our connection being set up. And then we can send messages from our client to the server just like that, pretty simple. Coming back the other way, we can set up basically a listener. There's broadcast client with a callback in there to our broadcast message. And when those messages come in from the server, we can do something on our client.
Easy. All right. So SignalR works fine, as expected, unless we actually push it under lots of limits, traffic. So when you hit your website with countless of users and hammered your website, it's actually not working as you expected. Some people believe that SignalR can handle unlimited connections. However, it is not really. It cannot. The reason is every server has limited resources in terms of CPU and memory, right? So when the clients, many clients, maybe too many clients, connect to the server, they actually consume the server's resources. And it means that at some stage, server will hit the maximum capacity. And as a result, it will fall over, which is fair enough. The thing is, persistent connections, which is the whole point of having the real-time functionality, persistent connections consume even more resources than normal like clients who connect to your website. I show you in diagram. So let's say this is the typical normal application. Client 1 connect to the server, send the request, and we'll get back the response and we'll go away. Second one, do the same. And the third one. So still, you see that there are always some room for other clients to connect, so it's not getting, overloaded so quickly. However, with persistent connections, you can see that the first one is connect, stay there, the second one, same, and then the third one. So the server, after a while, get quickly overloaded, and then it will be fall over.
So this diagram shows about 3 clients connecting to the server and it becoming overloaded. In reality, obviously, it's going to be a little bit more than that. How much more is a question that I wanted to know, and I answered that question with a tool called Crankier. Crankier is a load testing tool that comes with ASP.NET Core SignalR. You can check out the repo. It's pretty cool. What it does, it's both a server and a client. I raise up a server with my SignalR server on it, and then I raise one or more versions of Crankier, which will each raise a number of threads and hammer the crap out of the server to see how many concurrent connections we can get all at the same time. So I did that, and I did that on my local. I put on an S1 App Service, the Crankier server, and I capped out at 768 connections. Now, 768 is a very, very small number for me. I went and checked the limits on the Azure limits page, and it said that the S1 App Service has unlimited persistent connections, which is very different to that number 768. I then found out that actually what's occurring there is it's a per client limitation. So I needed to expand from just my local, and I did that with containers, because containers are cool. I raised 50 containers, and I pointed them at that S1 App Service, and I got 16,000 concurrent connections. That's a bigger number, and I was getting very excited at this. However, that limit on that S1 App Service for that per client connection is still affecting me here. So I needed to come off that app service, and I went to a VM. So now I'm running Docker on a VM. I've got the Crankier server inside a container in Docker in that VM, and I find my other 50 containers at it, and now I'm getting 65,000 concurrent connections. These are much bigger numbers, but still not enough for me. One of the issues that I found with containers is that I couldn't rely on how many concurrent connections each container could have. It's very easy to automate bringing containers up in Azure, but for some reason, some of them would cap out at about 500 connections. The rest of that 65,000 was catered for the rest. I don't know why that was, but to work around that problem, I switched out containers for VMs. Automating VMs in Azure at scale to do trivial tasks like this is a little bit annoying. I wrote a whole lot of PowerShell scripts that help me do that. Those PowerShell scripts are on my GitHub account for you to try as well, just in case you don't believe these numbers, or me. But You'll believe Nelly though.
Yeah.
But 100,000 connections was how much I was able to get with about 50 VMs pointed at one VM running SignalR service. That's a 2-core CPU on the server. At this point, memory and CPU are maxed. It's falling over. It's not stable. So let's start scaling that server and see how high we can get. So I went to an 8-core VM for the server. I got 214,000 connections. I'm only using about 80% of the resources of that of that VM at this point. I ramped it up again to 32, and I capped out at about 245,000 concurrent connections. That's as high as I was able to get one host, one server. I found a whole lot of weird things about Azure where, well, not weird, but some of you may or may not know that you can only open 20, by default, you can raise 20 CPUs per region. The way I got around that without requesting more was just to open 20 CPUs here, 20 CPUs there in different regions and that kind of thing. But 245,000 was the max that I got. It's not an amazing thing to do. I don't really recommend trying to get a server to just have 245,000 connections, but yeah, maybe Nelly can talk to us about that.
If you don't mind, I disconnected you from the slides. So we need a way to kind of manage this pressure when the clients are too many. We discussed that, so just recap that the app server will get overloaded by lots of connections, and then as a rule of thumb, what we do is just scaling the servers, right? It's good so far. However, with collaborative clients who wants to broadcast messages to the other clients, it's not really that easy. Given the diagram, the first client sends a message to the server, and the server knows about all the connected clients. So that will broadcast the messages to the clients.
Oh, what about those other ones?
They never get the message, unfortunately, because the app server too wouldn't have any idea about the other app services. So that's the problem here. The other clients won't get the message. As a solution, we have basically two solutions. One is traditional and one is modern. Please.
So I'll talk about backplane. A backplane is a way to propagate that connection information from those clients across the app servers that those connections were being made to, so we can solve that problem. It looks a little bit like this. We've got our app servers there. We've got our backplane in the background. What it's going to be is up to you. It could be Redis. It could be SQL. It could be your own custom-built one because that's what you like to do. And what that's going to do is end up in the message is going to come in from one of those clients. It's going to get pushed back to that backplane. There it goes. And then that backplane is going to be able to propagate it to our app server so we can set it out to those additionally connected clients. Installation and configuration of that is a little bit complex. And one thing to remember, certainly with SignalR on ASP.NET Core, is that sticky sessions are a thing. What that means is that if a connection comes in through to one app server, it must maintain that connection for the entirety of that client and server relationship's life. So we're additionally going to have to remember which client is connected to which app server and continue to communicate to them across those lines. That's not so great, Nelly.
No. So we are looking for a better managed service. So if we are looking for higher availability, higher scalability, and higher performance, that's what we should look at probably, which is Azure SignalR Service. So Azure SignalR Service as a modern solution, it's like very new product. It just came around last year. And it works as a proxy rather than a backplane. What does it mean? It means that all the persistent connections from now on are just delegated to the Azure SignalR Service instead of the actual web server. So the web server wouldn't take any persistent connection anymore, which is good. So we actually free up the server from the old connections. If I want to show you on the diagram, it's basically, so a server send a request to the client send a request to the server, But instead of sticking connection to the server, it actually gets back the URL of Azure SignalR Service. And then both client and server will connect to the SignalR Service. So basically, it just sits in the middle as a proxy. In order to broadcast the messages, it's much easier now. So SignalR sits between, and the data channel will be established from the client to the server through this server SignalR service. So the client will broadcast the message, and then it will go to all the servers, and then now on from the servers, it's easy. All of them knows about the connected clients, so the message is broadcasted. The problem is solved. If I want to show you on the network tab, so the flashback to our bidding application, this is the network. It's probably so small, so I just zoom in. So you can see that the first request from the client to the server is the first URL, which is the URL of the app server. But what we get back and what client is getting to connected instead is the second URL, which is the URL of Azure SignalR Service. So you can see that how this transition is actually happening. So the setup of the SignalR service is really easy. You just need to, you remember this code that we just showed you to inject the Azure SignalR, to ignore the SignalR service. You just need to replace this with Azure SignalR instead of add SignalR. And then you pass the connection string of the service to the code. Then the next code is same. Instead of using SignalR, you say use Azure SignalR. That's the only change basically you need to do. And that's it. So how to build the actual service? It's just through one single line of the code. So this is the Azure CLI. And you can run this command, and then the service will be spin up, and it's all good. You can use the ARM template instead, but that's a simple command. So to prove that the service is created, you just jump to the Azure portal. If you haven't seen, this is the Azure portal. You find your SignalR service that we just created, and you can see all the information about the service, like the log activities or any how many clients hit the service, and you can get the connection string as well. You can see here that you can adjust the unit numbers. What is the unit though? The unit is basically tell you how many connections this service can handle. It's based on the price that you pay. So SignalR basically scales by the unit. So each unit can handle 1,000 connections. And you cannot have more than 100 units. It means that in total, you will have 100,000 connections per service.
Now, as you saw on that little portal diagram, you can jump in there and with your fingers make that go up, make that go down based on how much you need. But a question that Nelly and I often get asked is, can we auto scale? And the answer is, yes, we can, but not by default. So we need to, the service itself doesn't auto scale, but we can use things that we already know about Azure to auto scale it ourselves. Two things that we might already know about ourselves, if the slide's going to move, and it does, is Logic Apps and Azure Functions. So I've personally written a Logic Apps solution to this. I have a colleague who wrote an Azure Function solution to this, and basically they're going to do the same thing. They're going to manipulate the Azure REST API. They're both going to do about these three things. The first one is to monitor this, call this first endpoint, which pulls the number of clients that are currently connected to that service. The next thing that we need to know is how many units are we currently using on that service. So we'll do a little bit of math to determine whether we need to go up or down, and if we do, then we'll use this last endpoint to make it go up or down as we please. Now, oddly, whilst the unit count goes up to 100, you can only set it to these values. You can try and make the REST API set it to another value, but it will not allow you to do so. So these are the values, only use those, please. Additionally, as Nelly alluded to, the price is per unit. So when you make the units go up, you pay more. When you make them go down, you pay less. Now, additionally, a little bit is that unlike just using a VM or whatever, There is pricing on the messaging as well. So we're going to want to make our applications a little bit less chatty than they might have otherwise been. However, one of the caveats of scaling down that Nelly and I have been whinging about for a little bit of time is that when you scale down, that unit price is attached to your Azure account immediately based on whatever you got to. So if I set a unit count of 50, for that day, I'm going to get charged for 50 units. So 50 times that price. Now, that's not amazing because it means that scaling back down during a 24-hour period doesn't really get you any cost saving. However, on Monday night, I raised 100 units in a SignalR service because that's how I like to spend my time. And then I waited for a couple of days for that to reflect on my Azure subscription, and I found that it only reflected about $3. That was very, very strange, so I got in contact with some people that I know at Microsoft, and they may or may not have officially said to me, unofficially said to me that that is changing. It's moving more to a consumption-based model. So that is a much better approach that I'm quite happy about. Hopefully we're going to hear an announcement about that soon, but you can try it yourself, and hopefully you'll see that it seems to be priced at the minute now rather than the day. So along with that price, something to be concerned with is whilst you might think, well, I don't want to pay that price, that's too much for me. The time that goes into setting up SignalR is very, very small compared to the time that it would traditionally take to set up the backplane. Additionally, depending on what your use case is, you need to be careful about how you scale those units. Sometimes increasing from 50 to 100, is not, depending on your use case, is not going to really have an effect. There's some great docs on docs.microsoft.com that will explain that. So read that before you start going crazy with your scale. Also, instead of scaling, you could just go serverless.
Oh yeah, that's easy. So let's go serverless. We talked about Azure SignalR Service, how it actually resolved some critical issues around the scaling when we have lots of clients connected to our website, which is good. However, we still have a few issues around, the best practices maybe. The thing is, SignalR Service, SignalR in general, is tightly coupled into ASP.NET. It means that if your company is not on ASP.NET technology stack, or if you are not a .NET developer, it means that you cannot really use this service, which is a shame. On the other hand, I show you the code, the ASP.NET code, and you probably realize that it's quite a monolithic code. Everything is just in a single bunch of code, including the connection management, including the hub class, sending messages, and probably if you have some database operations, it would be in the same code. So that's not really a good practice. We need to kind of break down this code to some like microservices. And serverless gives us this opportunity to move to microservices using the event-driven APIs. So do I have to be the .NET developer anymore? Really not, because you can use Azure Functions, and with serverless, you can write any kind of code you like, JavaScript, Java, Python, or whatever. So I want just to show you how we can switch to serverless, which is really easy, unbelievably easy. So you just jump to the website, to the portal, find your service, go to the setting, and switch the flag from the default to serverless. That's whole things you need to do for the service. Then you don't have any ASP.NET Core application anymore, so you need to replace it with some Azure functions. We actually, one function is definitely required, which is the negotiate function. What it does is client is connecting to this function, make a call to this function, and get back the URL of Azure SignalR Service. That's what the function does. It's a really fairly simple and small function. So the client will connect to this URL and connect to the server service. Potentially, you need some more functions to broadcast the messages. So you send like some message or content to your broadcast function, and the broadcast function will send it to all clients. That's simple too. I'll show you how this broadcast works. There is one point I want to draw your attention to. So with serverless in general, we don't have any dedicated virtual machine, right? So the code is getting executed, and the function will go away. So basically, you don't have any server anymore. So it means that the client cannot really connect to server and send messages to the server. It means that you are a little bit limited because this client cannot be collaborative, which is fair enough because you get some benefits from the serverless in terms of pricing and functionality, and you lose that the other functionality. So just want you to know that the clients are on listen-only mode. They cannot really be collaborative anymore, and you need to choose your scenarios carefully. So if your application is really chatty or like you have too many messages to broadcast, probably it's not a good way to do that. We came up with a demo that uses the serverless. So that's the flight center. So all over the world, whenever a flight is landed, all the connected clients will be broadcasted by the new content. That's probably one of the best scenarios that you can use. So you need to just find, like proper scenario for your case. How the Azure SignalR and Azure Functions work together? The Azure Functions offer a very productive programming model, which is triggers and bindings. So trigger is what makes a function to be executed, and binding is how to connect the way that one function connects to the other functions. So it means that how one function passes the data to the other functions or receive the data. And I'll show you how it works. So with our flight center, let's say there is a third-party API which kind of somehow populate the new landed flights into the queue. And then the queue now is the trigger. So the queue will trigger the broadcast function and pass the new flight. And then broadcast function has a binding, which is SignalR binding. You can have different bindings. You can pass the message to different, like resources in Azure. And the point is, you don't need to write lots of code, open the SDK for SignalR. It's just, I'll show you how easy it is. And the SignalR will broadcast it to the client. So the way you define the binding and triggers is like this. You pop into the portal, create your function, and then you say, the trigger is my queue, and the binding is my SignalR. That's it. And then the code for your broadcast function is basically these 3 lines. So you get the flight from the queue, which is the parameter. You can see it's yellow. And then you create a new object as per SignalR requirement. So SignalR required the actual message as well as the client event, which is listening to the server, basically. So you kind of like tell the SignalR that this is my parameters, and then assign it to your binding. And that's it. Nothing else, really. So it's Thursday night, and I think you're all tired, so I think you deserve some games. So if you go back to the application that we already scanned the QR code.
So I'm going to make that a little bit bigger, and I'm going to let you bring your phone up. If you haven't scanned in, please do so now. We've got a few players in there. We're going to have a look at some experiences that are going to show us the types of things that we can get away with real-time functionality in web apps. So go on.
Okay.
You got it? Good.
Yep.
So let's start with something very simple. I'm going to start with this thing. And if you look at your phone, you should have a little button on your phone. And some of you have definitely determined that that is the case. Some of you might also think that, no, I'm just making that up. So if we could all just stop pushing the button. Look at that. Okay. So what's happening there is you're pushing the button. You're all pushing the button. It's going up into Azure, into, interestingly, a Docker container, but we'll ignore that. And then comes all the way back to this browser and updates that number. So the faster you all push that number, the button, the faster it goes up. Now look at your screen, and I'm going to say this. So hopefully on your screen you've seen me type something. Now we're going both ways. So this is real time. That's, I think, a cool little example of bi-directional communication. let's get a little bit more funky than that. Let's ask questions to the audience. Do you like dogs or do you like cats? And wow, massive bias on the dogs here.
I've never seen this much difference.
Generally, the audience is split in two. Some people are confused. That's why we're seeing a lot of, like this is real time. Generally, if I was doing this, I don't know, for real, I guess I would throttle this to stop that from being a little bit annoying. But I want to show that, or I want you guys to feel how like what the latency is. Basically, and we'll find that again with perhaps this one. Mm-hmm. Now there's a little shape on your screen, and every time you push your finger down on that, it highlights your name somewhere on the screen, and when you release it, it releases it. So each one of those is just one message that's being sent across that persistent connection that we've got. Hopefully if you can see your name up there, then you might get a feel for what the latency is like. The Wi-Fi in here is not amazing, so I have detected some milliseconds of latency on that, but otherwise most of you should be feeling a latency of no more than, let's say, 100 milliseconds or something like that, or less, let's say. Anyone feeling like half a second of latency or anything like that? No. Something that's probably a little bit less silly is something like this, where I might stand in front of an audience and say, are you from Sydney? Look at that. Ooh. So there's quite a few people that aren't from Sydney. Have you ever raised a Kubernetes cluster? Look at that.
Mm. Have you ever used SignalR? Yes,
SignalR users in the house, about 50-50. Have you ever used SignalR Service? I was going to say raise your hand. You don't need to raise your hand. You've got a device in front. No. Okay, so there's a couple of people that have. That's cool. So let's try something even a little bit weirder. I'm not actually going to tell you how this works. I'm just going to see if you can figure it out. And I think that Red is a little bit slower in figuring out, but Red's got it. So if you're not connected, I'm going to tell you, or I'm going to explain to you what's happening. Basically, everybody who is connected has two buttons on their screen, and those buttons are the color of one of those little bats. And if you push the top button, your bat goes up, and if you push the bottom button, your bat goes down. Now, if there are 10 people on the blue team, then every time you push your button up, that means 10% of the bat goes up. So it's a teamwork exercise. If you don't like your team, you can push the other way, and you will make your team lose.
Maybe just make it a bit faster.
Interestingly, with this experiment, is that I didn't, even though this is a team, oh, that's too slow. A little bit faster. There we go. Interestingly, though, that this is a team experiment, you all kind of worked out how it worked without being told. Blue is definitely smashing it. Red needs a little bit more teamwork. There we go. Look at that. We can make it even perhaps a little bit harder for Red. Why do we keep making it harder for Red? We'll keep going to blue. We'll go to blue. There we go. Get that blue. Oh, Blue's got that.
Yeah.
Has Red got it? Oh, yeah. Look at that. Oh, yeah. Look at that.
We're getting there.
Awesome.
A bit wider.
What's that going to do? That's just going to make it fatter. That's not going to do much.
Doesn't work.
Maybe I think we need a lot more difficulty. So something like this, let's say. There's no way. No way. Too hard. Okay. So another little idea that we'll look at is called on this thing idea wall. If you've got your phone in front of you, you'll see that you can type things in there, and when you type things here in there, it will pop up here. Look at that. And there's in the shape and maybe of the color of little post-it notes, and look, I can move I can move them as well, like little post-it notes.
It's good for retro sessions.
I can move the board around and this kind of thing. Nelly, buy me a drink.
Okay.
I think the drinks are free later.
I want a drink.
Free pizza for all presenters. Thank you. That's very kind. Very much unlike post-it notes, we can do this and find out who wrote all those things as well. So we'll just check to see if any Bert. Prawn I said Bert. Yep. Okay. So just a recap of what's happening here. Every time you're sending these messages, it's going into the cloud. It's going to a SignalR server, and it's coming back up to this presenter device. So if you haven't used SignalR before, now you have. I think that probably is the end of this demonstration.
You can actually go back
You do
to
that.
the slide.
I don't know how computers work.
Okay. So we actually provided all the, that's easier. We actually provided all the references for you. So everything is in our weblogs. So I provided some serverless things and the general things about Azure SignalR Service and all these detailed things.
I've got a whole lot of scripts and whatnot to automate VMs in the cloud to get loads of persistent connections and that kind of thing, a whole lot of blog posts. Additionally, that digital icebreakers game thing that we just played around with, you can get that from my blog as well for free. Do crazy things with it.
So yeah, and if you have any question, please ask and enjoy the rest of the night with the party. Thank you.